So I think we'll make a start now. It's a couple of minutes past 5. So good evening, everyone, and welcome to our second webinar as part of our VarsityCode sponsorship. And so for those of you who missed the webinar last week, which was our grad Q&A session, I'll shortly be posting a link in that. Well worth a watch to hear some of the experiences of our latest grads who joined us in September and to explore career opportunities within the bank as well. I'll also share links to our graduate and IP application vacancies that you can take a look at. And we've also got a number of grads online on Discord should you have any questions on as well. One more fun reminder before I hand over to Robert and Daniel is just around our coding challenges for the VarsityCode League. So make sure you take the opportunity to take part, and we've got some great prizes on offer. So yeah, get involved and we look forward to seeing how you get on. So yeah, on to tonight's session. So I'm absolutely delighted to welcome Robert Callender and Daniel Rard. They're going to, over the next hour or so, going to be talking us through why Python is great for machine learning. So they'll be giving us an overview of machine learning and then discussing some use cases within Lloyds itself. So without further ado, I'd like to hand over to Robert and Daniel.
Thanks, Justin. Happy to be here. Hi, everyone. I'm Robert Callender, a software engineer in Lloyds Banking Group.
And hi, yeah, I'm Daniel Rard, and I'm a graduate software engineer.
And today we're going to be talking to you about Python machine learning. Now, in this talk, we're going to be covering we're going to be covering a few things. As you know, I'm sure you've heard, Python is a very popular language behind only C and Java, and part of the reason for that is its explosion in popularity with machine learning experts and data scientists since about 2012. And today we're going to explore why that happened. So in this session, we're going to cover what is machine learning, why Python is great for machine learning, some of the Python machine learning packages that are available out there. Then Daniel's going to take us through a use case of Python machine learning here at LBG, namely customer carbon emissions, and then I'll give you a demo a live demo of two linear regression models. So now you might ask, what is machine learning? Well, we've got a pretty good definition here that Tom Mitchell came up with in 1997. He said that a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improves with experience E. Now that may seem very complicated and abstract and kind of mathematical, but really all it's saying is that to learn is to improve at a task as you gain more and more experience with it. And I'd say that's a pretty good definition of learning, whether it's being applied to a person or to a machine. Though do bear in mind with experience E there, the term experience is used rather broadly, and in some types of machine learning, E is more closer to data really, rather than what we'd consider experience. Now, if you don't believe me that this definition can be fitted to human learning, then let's take an example of learning that most people do, namely learning to ride a bike. So, don't know about you, but I kind of learned to ride a bike when I was about 8. I went to the park with my dad. We went to the top of a hill, put my helmet on, put me on the bike, pushed the bike down the hill, and yelled at me to pedal, pedal, pedal. And fingers crossed, gravity and adrenaline would teach me the rest. And I crashed pretty quickly, not after very long at all, and came off the bike. So we went back up the hill and did it again. I crashed again. But as the day wore on, I gradually began to stay on the bike for longer and longer. And actually, by the time it was kind of late evening, I was actually staying on the bike indefinitely. In other words, I had learned to ride the bike. Now, we can fit this to Tom Mitchell's definition there by having the task T be riding the bike and not falling off, experience E being the amount of time spent practicing riding the bike and trying not to fall off, and the performance measure P is the amount of time I could stay on the bike without falling off in one go. And as I said back there, clearly, as I gained more experience E, as I practiced more riding the bike, my performance measure P improved. I could stay on the bike for longer in one go with respect to that task T, obviously riding the bike and not falling off. In fact, in terms of machine learning, the type of learning I was doing there as a person when I was riding a bike is actually called reinforcement learning. So reinforcement learning is when you take an agent, so in the case of that example, me, put them in an environment, so in that case, the park, You give them a series of actions that you give them a score that they're trying to maximize. So that was P in this case, that was that performance measure, the amount of time I could stay on the bike for without falling off in one go. And then you give them a series of actions, a series of actions they can do, which either increase the score or decrease the score. And through trial and error, the agent learns and forms a strategy around trying to repeat, obviously, the actions that increase the score and trying to reduce or avoid entirely doing actions which decrease the score. Now, it's not just reinforcement learning that's a type of machine learning that humans imitate. Another type of machine learning that humans imitate is supervised learning. So supervised learning is when you take a machine and have it be supervised by a data scientist. Now, what the data scientist does is they give the machine a series of inputs known as training data and outputs known as target values, and they basically leave the machine to kind of try and infer patterns and relationships between the inputs and outputs. Then, once the machine is finished kind of inferring, the data scientist will give the machine a new bunch of inputs known as test data, and they'll see what outputs the machine gives for the test data, and whether those outputs are kind of sensible or not. So an example of people doing supervised learning is when, as children, we learn multiplication at school. So obviously, in this context, we, the children, are the models. The teacher is the data scientist or the supervisor. And if you think of your times tables that you're given as a child, what comes on the left-hand side of the equal signs, so things like 1 times 1, 2 times 2, 3 times 3, 4 times 4, those are our training data. And then what's on the right-hand side of the equal sign, so 1, 4, 9, and 16, respectively, those will be our target values. Now, and as children, so then what happens then as children, by memorizing these tables, by inferring patterns within them, and by understanding how multiplication works, we are able to learn multiplication. And then as adults, we can do multiplications like 1.5 times 2.5 is 3.75, even though that's not a multiplication that appears anywhere on any times table. So you might go, well, okay then, so if humans can imitate all the type, machine learning, then why on earth is all these, do we always hear about huge amounts of resources and effort being put into machine learning? What's the point? And what I'd say to that is that due to their greater memory capacity and learning speed, machines will come up with actions and strategies that people ultimately never could. So take, for example, in 2016, when Google's AlphaGo program was playing the world Go champion at the time, Lee Sedol. Now, during their second match, AlphaGo made a move, famously known as Move 37, which Lee Sedol, for the life of him, just could not understand why it had done it. He was just thinking, no right-minded Go player would make this move. This is just surely wrong. However, he was actually in the wrong. AlphaGo was making this move as part of its broader strategy and ended up winning the match, while Lee Sedol lost because he couldn't understand what its broader strategy was and thus couldn't formulate a counter strategy, given that obviously AlphaGo as a machine was creating this strategy due to its greater memory capacity and learning speed. Now, it's worth bearing in mind that, as I say, machines will learn actions and strategies that people never would, and sometimes that'll be worse than what a person does, and that'll have negative outcomes. But a lot of the time, what a machine will learn will actually be better strategies, better actions than what a person would learn, and that'll have beneficial outcomes for us all, like with AlphaGo and Lee Sedol there. Now, that's just putting machine learning a bit to one side there. Let's actually talk about some Python. So why is Python great for machine learning? Well, a lot of the reasons that Python is great for machine learning also come back to why Python is just a great programming language anyway. So for a start, Python is very easy to use. It forces you to indent your code, so it's easy to read. It uses plain English keywords for its built-in functions. You also don't have to worry about putting colons at the ends of lines of code or surrounding code blocks in curly braces, so you're less likely to get runtime errors like that with Python. Also, Python is what's known as a general-purpose programming language. So what this means is that anything you want to do in software development, whether it's query a database, put data on a web page, or even just run a function, you can do it with Python. That's as opposed to a domain-specific language like R, which can only do certain things. So, for example, R cannot put data on a web page. So say you wanted to do some machine learning process where you queried a database, did some machine learning on the database, and then stuck the results of your machine's learning onto a web page. You couldn't do that all with R. You'd have to integrate R with another language, a language that had some kind of front-end capability. And obviously, it's going to be a lot more hassle to do the same process if you have to use two languages and integrate them together, rather than just using one language like you can with Python. And I'd say then finally, the great thing with Python is it's always been open source since its creation in 1991. This is opposed to R, which became open source 2 years after its creation in 1995, and Java, which became open source 11 years after its creation in 2006, I believe. What this means is that there's a huge number of Python packages out there, and thus a huge number of Python machine learning packages. So if you're dealing with some kind of tricky machine learning problem in Python that you're trying to code for, rather than having to code it all from scratch, most of the time you can just import the Python machine learning package or packages that you need, and they'll have the methods and or constants that you require. What being open source for Python also means is that if you want to see some bug fixed in a machine learning package, or you want to see a feature added to one, then you can just talk directly to the person working on it, and they can kind of fix it for you ASAP, rather than being bound to a company or a proprietary timeline. Now, there are a lot of Python machine learning packages out there, as I said before, but the four we're going to look at today are NumPy, Pandas, Matplotlib, and scikit-learn. Now, probably the thing that immediately jumps out to you there is, hey, wait a second, it's only scikit-learn that's actually a machine learning package here. The other ones, NumPy, Pandas, Matplotlib, they've got other purposes. Why are we using those? And to that, I'd say, well, in order for a machine learning process to work properly, we need two things. We need good, clean data that the model can understand and learn from. And we also need a way to represent the results of the machine's learning, so we can tell whether it's going in the right direction or not. So if we come back to the example of children learning times tables, say you were given, rather than being given to learn multiplication, rather than being given times tables, you were given just a jumble of multiplication signs, equal signs, and integers. You wouldn't be able to learn anything from that. The exercise would just, be pointless. You'd understand nothing. And that's where NumPy and Pandas come in for machine learning here, because they they put the data in a form that the machine can understand. Now, if we kind of flip the point of view here and consider the teacher in this kind of supervised learning example, when it comes to figuring out whether you've actually learned multiplication or not, they can't just take your word for it. They have to test you in some way. They have to see you attempting to do multiplication and see if the results of that are correct or not. Now, obviously, in school, they'd use things like test papers for that. But in machine learning, we use Matplotlib for that, as Matplotlib allows us to plot the results of a model's machine learning onto a graph and see whether it's going in the right direction or not, or the model needs some tweaking. So now I'm going to hand over to Daniel to take us to talk about how Lloyds Banking Group is using Python machine learning. Over to you, Daniel.
Thanks, Robert. So yeah, hi everyone. I'm going to be taking you into a deeper dive into how we might use machine learning here at Lloyds Bank. So usually there has to be a reason to use machine learning, and that's usually based on a use case. And so for this particular case study, we're going to be talking about predicting customer carbon emissions. So why might we do this? Well, there's a growing number of eco-conscious businesses, much like ourselves. And over the past several years, Lloyds has committed to becoming more sustainable. This is emphasized by our deep involvement in COP26. We recognize the vital role we must play in supporting the UK's transition to net zero, and have set our targets and goals in accordance with that. So as you can see here on the screen, by 2030, we want to halve our carbon emissions, which are quite ambitious goals. So what's the task we are looking to achieve here? Well, we can follow the sort of task, experience, and performance measure template which Robert set in the previous slides. So our task is estimating customers' carbon emissions. The question we really want to answer is, can we use the customer's transaction data to automatically estimate our customers' CO2 emissions? Now, by customer, we're not talking about individuals such as you or myself. We're talking about more larger commercial businesses. Why might classifying customer sectors be useful and customer CO2 emissions? Well, it potentially provides the benefit to customers it allows us to potentially provide benefit to customers who are more eco-friendly and net zero themselves, and allows Lloyds to employ its funds in a more sustainable way. Can we go to the next slide, please? Thank you. So we're going to be looking at data science in terms of, there's the data scientist side and the data engineer side. So what is data engineering? A data engineer constructs data products such as pipelines and dashboards for business use cases. This is the process of organizing and formatting data and automating much of the process. This is to make it easier for other systems and people to use and understand data. It really provides the sort of backbone of data science. So being resilient, scalable, and future-proof is key. Now, why is this necessary? Well, the data could be incomplete. There might be missing fields. There might be missing parts of the data which need to be fixed. Alongside that, imagine how long and tedious the process would be if we have to take Excel spreadsheets containing data and send it to different sides of the bank for the other teams to work with. This process would work much faster if it was automated. And so that's what a data engineer would do in building the pipeline. The data might also be human readable. And while this is good for me and you, it requires a computer a lot more processing to understand. So feature engineering and encoding become important here. So let's go to an example. Here at the bottom of the screen, we can see the customer carbon emission pipeline. The initial step is to get the customer data, similarly to what we were talking about in terms of the automation. We use internal tools to get the transaction history from our customers and stream it into the pipeline. The next step would be to clean the data. We ensure we remove data that has missing element fields or isn't necessarily relevant. The packages that Robert mentioned earlier, such as NumPy and Pandas, becomes extremely useful here. Finally, we get to the first part of the model, where we're going to be predicting whether or not someone is an individual or a business. Once we have found the business, we can use a government API to fetch even more data from an API such as Company House. This increases the confidence in our model and ensures that the highlighted customer is in fact a business. Once we figure out who the businesses are making transactions to, we can ultimately predict the level of CO2 emissions, as we can classify their sector and use the historical data from the sector to figure out what it's most likely to be. And then finally, one of the most important parts is developing the reports and the governance to ensure that we make the correct business use cases. Next slide, please. So let's get on to the more glamorous side of data science, which is actually creating the models. Here, packages like sklearn and TensorFlow help data scientists to build and improve models, which takes data from the pipeline and converts it into a useful statistic, which can be made into a story for both technical and non-technical audiences. So there are really two main types of predictive sections, which can be classification and regression. So we're going to go first into a classification model, which is actually called logistic regression, which might confuse some people. Logistic regression helps predict what category something is in. An example of this may be if a payment was fraudulent or not, or perhaps an email being spam or not spam. So it can be confusing that it's called logistic regression, and this is because logistic regression is based off linear regression, yet the classification comes at the end of the algorithm when the output is squashed between 0 and 1 to make a binary classification. So as you can see on the graph, it's either a 0 or a 1. In our use case, we use logistic regression to help predict which sector a company is in, or more specifically, whether it's a high carbon emission company or not. There are other models, such as support vector machines and neural networks, which can predict multi-class classification problems more effectively. This is to predict whether, for example, a company is in a fishing sector or an electric vehicle sector, or perhaps agricultural sector, and many more, because it can do multi-classification. Once we've predicted what sector a company is in, we can then go and use linear regression. So what is a regression? A regression algorithm is an algorithm which is trained to produce real number outputs. So for example, we can predict the numeric amount of rainfall in a forest given the temperature in the area. So in our use case, once we know what sector a company is in, we want to estimate a numeric value of how much CO2 is being output. So given the independent variables, such as the sector, the amount of money in the transaction, the amount of customers a company has, information which is all added and cleaned and developed during the pipeline, it can output the predicted dependent variable, the CO2 emissions. This information, as mentioned previously, can then be used to help Lloyds make business use case decisions following the model's output and data analysis. And so this was the last section in the pipeline, which is the governance and the develop report section. So at the bottom of your screen, you can see a little snippet from sklearn on how quickly and effectively you can make a linear regression model in Python. So I'm going to pass you back to Robert, who's going to take you through a full demonstration.
Thank you, Daniel. So yeah, as Daniel said, I'm going to take you through a live demo of two linear regression models, one of them complex or multivariate, and one of them is simple or univariate, and they're going to be working on a data set about wine. So if I just go to my code here. Right, so I got this data set from UCI Open Datasets, and it covers about 1,600 different wines, various different characteristics of each of those wines and the quality they are assigned by a panel of judges. Now, as you can probably already tell here, we've got an awful lot of different characteristics of wine. We've got fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, alcohol, and quality. So, so these those 11 will be our predictors, and then our quality here will be our predictant. Now, as you can probably tell here, yeah, that's a lot of predictors, so we're going to need to use complex linear regression. Another thing to bear in mind is that for our test row, we are going to use, or our test data, we're going to use this row here, and it's assigned a value of equality of 5. So we're going to need to see how close to 5 the complex linear regression model predicts. So first, if we go to the code for the complex linear regression model here, so you can see that just kind of removes the headings from the file, from that text file, because obviously we don't, you can't just feed a heading into the regression model. That's just not going to work. We then extract the data from the file, we convert it to a NumPy array, and then to a pandas data frame. After that, now this is a very important bit here, we're going to try and remove the test row from the data frame. That way, because you don't want to have the test data within the training data. No one ever learned anything by being given the answers. From there, what we're going to do is we're going to look at the data and select what's in the predictors columns as our training data, what's in the target values as our and what's in the quality column as our target values, and then we're going to feed them into this linear regression model with this .fit method, and yeah, it's going to learn from the training data and the target values and create a line of best fit, and then we're going to return that line of best fit. Once we've done that, we're going to use this .predict function to run the linear regression model on the test row and see what value it predicts for our test row, what value it predicts for the wine quality. So let's just run that, and hopefully it's something close to 5, but we'll see how this turns out. second, let's just, okay, there we go. Yes, so the value we get here is 5.21, which is not too bad actually. That's pretty close to 5. And as I say, we're using 1600 rows there, so yeah, that's a pretty good prediction. Now if we gave it less rows, so for example gave it something like 200 rather than all those 1600 rows, we'd expect it to have a less accurate prediction. We'd expect it to something a bit more like something further from 5. There we go. So yeah, value about 5.267, which is yeah quite a fair bit further away than when we had 1600 rows being fed into the model. And if we put something in the middle like 800 rows, should get a prediction value in the middle. And we do. It's about 5.23, almost 5.24. So yeah, we get. So that's another important thing about machine learning to kind of emphasize there is you'll hear about this mad rush to put as much data as we can into machine learning models. And the reason for that is the more data you put into them, the more accurate predictions they're going to make. However, I was wondering, would it be possible to use simple linear regression here? Would it be possible to take to figure out a best predictor for the wine quality? In other words, a predictor which, when changed, would be most likely to affect the wine quality, and then just use simple linear regression from there. Would I be able to predict a better value for the wine quality? Well, as we find out, the answer to that, as to what's the best predictor, will surprise some people and really not surprise others. So if I go to the simple linear regression model now and run that, so what I did here was I created a collinearity matrix, and that'll tell us how each predictor correlates against the quality predictant. And we're looking for the predictor whose value is furthest from 0. It doesn't matter whether it's positive or negative, but we're looking for the value furthest from 0. So fixed acidity correlates with a value about 0.131, volatile acidity minus 0.39, so that's pretty good. Citric acid, residual sugar, chlorides, they're not as good as volatile acidity. Same for free sulfur dioxide, total sulfur dioxide, density, pH, sulfates. But for the for alcohol content, it's actually better than volatile acidity. It's the best predictor of wine quality. So you heard it here, folks. Alcohol content is the best predictor. If you want to know, if you want the best indication of how good a wine is, you look for how drunk it makes you, basically. As I say, that will surprise some people and not surprise others. So if we then go to move this and create our create a graph of alcohol content against quality, what we're going to get is well, we'll see how well the value it predicts compares to the complex linear regression model. As I say, this is being given with 1600 rows, by the way, so that's why it's taking a little while. It should come up with the graph. Yep, here we go. So here we've got quality against alcohol content. As you can see, the points have a generally positive skew to them, so that's good, and so does our line of best fit. And also the line of best fit created by a simple linear regression model is going through some points, so that kind of stands in its favor. But as you can see, there's not it's not as steep a positive gradient as the points are suggesting, so it's not perfect. And if we look at our prediction here, it actually says 5.41, so that's that's a lot further than it was for the complex linear regression model, even though this had 1600 rows. When you compare it to the complex linear regression model had 200 rows, that predicted 5.26, so it's much less accurate with just trying to find the best predictor and use simple linear regression. So again, that brings forth another important concept, which is that you can't kind of cut corners if you've got a multivariate data set with multiple predictors and try and find the best predictor and then use simple linear regression. You have to use complex linear regression. So that brings it to the end for me. Now I'm going to hand over to Justin to talk about the IP and graduate schemes available at Lloyds Banking Group.
Yeah, so this is just a quick reminder of the schemes available. So the software engineering scheme is open now for applications. I've shared the links in the chat, so you should host, I'll repost those as well, and also remind you of the industrial placement ones. As I said earlier, the deadline for that is in 5 days' time, the 30th of November. So if you're interested in those, then you get your applications in now. We're also on Discord as well, so if you've got any questions about these, we've got some grads on hand to come and answer those, so feel free to post your questions there. And then back to today's session. So if you've got any questions that you want to ask Daniel and Robert, then please post them in the chat and we'll get to them.
Thank you for listening, everyone.
I think there was one question about linear regression versus complex linear regression. Could you just explain what the difference is between the two of them?
Yeah, so the kind of basic the difference really is that so linear regression, it's trying to plot a line of best fit using say the target data and the training data and the target values. And for simple linear regression, you just have a one-dimensional input to worry about. Basically, it's just scalar values you're dealing with and then a scalar output. While with complex linear regression, you're getting your input, each input basically as a vector. So with that example with the wine there, it had, you know, each element, each record in the data set was a vector, if you like, because it had all those different values for alcohol content, volatile acidity, and so on. So that's why that was better to use multivariate or complex linear regression there.
Thank you for that.
Cool. So last call for questions. If not, then a massive thank you for everyone for joining us for tonight's webinar, and thank you for taking part in the VarsityCode competition. Reminder that our competitions, our coding challenges are open till next Wednesday. So if you hadn't a chance, then take a look. I think some emails come through from Show Code. So also details on Discord as well. So you get involved. And finally, a massive thank you to Robert and Daniel for taking us through today's presentation. So thank you, and wish you all a good evening.